once again, welcome to the lecture number 3 of the deep learning course. In this particular session, we are going to talk about some convergence proof that we have seen in the last class. In the last class, we have seen that there was a method by which we can find out what is the right parameter. So let me tell you formally that in the last class, we were discussing about the classification problem, okay? We were discussing about the classification and there the classification the classes were two classes, means +1 and -1. These were the two classes. What we had that for a given item we were talking about credit approval problem where there was some person and he was having some x1 x2 x and n number of attributes, so maybe age and maybe his salary, maybe other factors. And then since we wanted to model the problem as a linear model, so we thought that there should also be some weight, and weight could be w1 w2 dot 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 wn, and weight should be there. And we have devised an equation that says that we are going to multiply term by term, and we say that w0 x0 plus w1 x1 dot 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 plus wn xn, where w0 is the thresholding, it was with respect to the thresholding term. And we said that actually we want to see that what is the sign of this particular quantity to tell that what is the classification of that particular item. So this thing we have covered in the last class, and in the last class we have also seen that this particular thing can be written in a very simplified form like this, that we want to see that what is the sign of this summation term. A vector notation also we have studied that says that W transpose X, where W and transpose are W and X are actually treated as a vectors, and then the same quantity can be obtained by having the W transpose X. We have identified that this represents a decision plane or a hyperplane where one side the things are positive and other side the things are negative. So this we have seen in the last class. We have also seen that if the data is there, for example, let's assume one class is here and another class is here. If we shift it somewhere, then there is no problem. There is no issue in terms of the problem representation. The problem representation of the problem remains the same. It is again the classification problem, and it doesn't becomes more difficult or more easy by doing all these things. So these mathematical convergence, where we either transform all the data, means either we shift to the smaller size, means we do a scaling, or we translate, and some points are here, some points are here. All these translation and rotation, and scaling, all these things are actually not going to have any effect in terms of the classification problem difficulty. This we have seen in the last class. So now in this particular session, I would start by asking this particular question, that that let's assume that we have a coordinate system where the dimension is actually equal to what is the dimension of the W. Then if I pick any W, for example, let's assume that I pick 0.1123, any W. If I pick any W, so what would that W be? That W be a point? Okay, that W be a point. If you actually connect that W with the origin and draw a perpendicular on that, then this perpendicular line is going to be your decision boundary. Means one-sided item are the positive, and other side items are the negative. How come it is going to be? So I want to say you this by giving a small understanding to you, mathematical understanding. Let's assume that there is a point P on this. Okay, so and assume that the P has a prop P0, P1, P2. It is a vector of, it must be a vector of that particular kind. So if I put this thing into this equation, like actually the right equation that is here, what you get? You get I think W0 P0 plus W1 P1 plus W2 P2 dot 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 WN Pn. Okay, you get this quantity. What is the value of this thing? This value must be 0, because you know that this point is on the plane, and this is the equation of the plane, so this value must be 0. If I want to find out what is the angle between let's say that it is origin, what is the angle between OP and OW? Let's assume that this point is W. What is the angle between these two things? If you want to find out the angle between these things, so you know that there is a formula that says cos theta is equal to OP dot OW divided by OP dot OW. Okay, these norms. So here, this dot product that you are going to get is actually this particular quantity because term by term multiplication. So what is this value? So you have seen that this value is 0. So if I put 0 over here, this complete equation becomes 0. So this part becomes 0. So the angle between these two things, the vector and any other point which is on the plane, becomes 0. So can you tell me what is the theta? What is the value of theta? You know that at the 90-degree angle, the cos theta is equal to 0. So what does it mean? It means that OP and OW, they are actually perpendicular. So this weight vector actually that you are going to achieve is a kind of perpendicular vector on the decision plane. Make sense? Is it clear? So this is a perpendicular vector on the decision plane. Now I want to draw your attention to another point. Let me just quickly clear this and tell you that particular thing. And let me cut it. So another point that I wanted to make it. Let's assume that this is the coordinate system and there is some plane. Okay, this plane is actually passing. 1 minute. I have drawn. So it is passing through origin, and now I just said that if there is some W, if you draw that, it would be a perpendicular on the decision plane. Now this is a W. Okay, I said that this is a W, but there is other point also. If I take this as a W, will this also be a perpendicular on the same plane? Yes. Will this also be perpendicular on the same plane? Yes. Will this point will also be perpendicular on this plane? Yes. So if I want to find out the right value of the parameter, means W, so there are multiple such W's exist. Okay, not only one W, there are multiple W's exist. So how many? Infinite number are, because all the points which are there on this particular line, you can take it as a right parameter. So this is not a very difficult problem, difficult thing to see. Just see that if w0 x0 plus w1 x1 dot 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 wn xn is a formula. So if I say that c multiplied by w1, c multiplied by w2, c, this is another formula. Since the equation of the previous thing was 0, then by multiplying c also, it is also going to be 0 only. So there is not only one w, there are actually infinitely many w's which are actually possible. So into the computer science domain, into the ML domain, most of the time it is because we want to find out a unique parameter in some way, because system is going to hunt for a unique parameter. So sometimes we say that this W that is going to given to me, I want that norm of that W should be equal to 1. It is an extra condition, and this also does not have any effect on the classification boundary or the problem or the machine learning problem. This also does not have any adverse effect on the classification or the machine learning problem as such. But what it ensures is that you are going to get a unique kind of W for which you are hunting. So actually it actually says that I would pick only that particular W whose norm is actually going to be 1. So it would be a unique W with respect to my understanding. So most of the time, however, I am not going to write that mod of W is equal to 1, but we assume that mod of W is actually going to be 1. And we can, and even if somebody is not mentioning that, you can think that whatever parameter he is coming up with, those parameters can be transformed to such a system where the mod of W is equal to 1. And it is not very difficult, because you just find out the mod and divide all the parameter with that particular mod. All right, so this was a small mathematical background that I wanted to tell, and now I wanted to bring your focus to the actually what we are doing, the classification. So I have given you an example. I had told you that let's assume that this is the system where this is a negative point, these are the positive points, and these are the negative points. And let's assume that because you don't know that what is the right parameter, you randomly picked, or somehow you initialize, and you actually end up with this particular decision boundary. Okay, in the last class we have discussed, let's assume that you somehow initialize and got this particular decision boundary. My question is whether this decision boundary is right. The answer is no, because you can see that this negative is up, this positive is down. So how can this is the right? It would be nice that if you can find out a parameter with respect to this particular line. So I have to change it. Okay, and where you can see that this is the perfect line. However, this perfect line is not single. This line would also be perfect, this small deviated point, this would also be perfect. So multiple lines are there which are actually correct. Okay, so how can we find out any one of them effectively? How can we efficiently find out any one of them? This is the my question. And in the last class, I told you that we are going to utilize a specialized method, and that method is this, that if you want to do a learning, use misclassified example. Use misclassified example. So in this, because this was the, let's assume that you are into this particular scenario, you want to reach to this scenario. So who are the misclassified example? This negative, because these are okay, these positives are okay, these negatives are okay. So who is misclassified example? This positive is misclassified example. Use that misclassified example to update the value of w's. How many w's you have depends upon the how many dimension you have. So based on the dimensions, you are going to have the w's. So this w would be maybe w0, w1, dot dot dot, wn. So each of them you are going to modify. Let's assume, let's focus on the ith w, that I want to find out what is the right value of ith w. Okay, I want to, let's just focus on one of them. So it is, the formula is saying that you use the previous value and add something to that. What you are adding? You are adding for there is an alpha. Alpha is just a constant. It is just trying to understand that what is how fast you are going to learn. If the value is large, you are going to learn very fast. If the value is small, then you are going to learn slowly. So definitely you would like to have a large alpha. But the problem is this, that let's assume that you are sitting in Delhi and you want to come to the Pilani. So how fast steps you can take? You can take the 1 kilometer steps. For example, in every step you are going to take one step. But if you are standing just in front of the gate, then you cannot take 1 kilometer step, because if you are taking I think let me change this 1 kilometer to 10 kilometer steps. So let's assume that you are coming from Delhi to Pilani and you are taking 10 kilometer step. In every step you are going 10 kilometer. So what would happen, that if you are far away, then you can take the 10 kilometer things and you can reach to the gate. But after the gate, when you are near to the gate, if you again take the 10 kilometer thing, then you would be out, you would be going out to the BITS Pilani, and you would be into the next side of the BITS Pilani. What would happen? There also you would take the step and you would again reach to the same point. You would not be able to enter. So this alpha should be chosen effectively, so that you can you can slowly get near to the point. So sometime people, what they say, that there are other methods also that say that adaptively I am going to reduce this value, but that is a different techniques. It is very difficult that where is the optima. Based on that, then only we can decide that. And since we don't have any idea that where is the optima, it is suggested that you take a smaller step. For example, you take only 1 meter step. So from the Delhi, it would take so many time to reach to the gate, but after that, after entering to the gate, you would be able to come inside. Okay, so this alpha is going to be a small number that actually controls that how much I am going to add, and this is actually going to define your learning speed that need to be controlled. So again, what is the second part? The second part is y and xi, yk xi. Okay, yk into xi. So this you are going to do, and add to this thing, and I am going to tell that this is going to work. You may be asking, sir, how come this is work? What is the reason that this particular thing is going to work? Let me give you an intuition. Okay, so this as I told you, that you are updating all the parameters, and then the parameter would be such that things becomes good. Let me give an example. Let's assume that what is the value of y and what is your summation term or the estimation is going to give you. Once again, okay, let us try to understand that what is the actual y and what is the summation term is going to give you. Okay, so let's assume the y item is positive. Item could be positive or negative only. Now only these two cases are there. And what is your summation? Summation could be positive and negative. Then it is right. And if it is right, then you are not going to change the parameter. Okay, because I am telling that you are going to change the parameter only when the things are misclassified. Whether it is misclassified, no. So these cases are fine to me. Another cases are when +1 -1 is there, and I say that my system is to the +1, it is my system is telling -1. To the -1, my system is going to tell me +1. These two cases are the problematic cases. This is okay. These two cases are the problematic cases. Means in which I'm going to learn, I'm going to modify the things only into this particular scenario when actual label is positive, but my by doing the summation and by doing the classification, I'm going to say -1. This is the case. Make sense? Let us try to understand what happens in this particular scenario. If summation, if the y is positive, in this particular case, what is there? That y is actually positive. Y is actually positive. So this value is positive. Everybody understand this value is positive. What is this value? Plus v, positive. Okay. Everybody, can anybody write yes, that you understand that this value is positive? Because this is the case that I'm considering. Now I'm considering that y is positive. If the y is positive, alpha is also positive, we know. This value is also positive. And what is the value of x? What is the value of attribute? Few minutes back we have discussed that we can always assume that all the values are positive, because we have seen that any translation is not going to affect. So let's assume that this is also positive, and let's assume that it is a fair assumption, there is no problem in that. That let's assume that we have done this kind of transformation and all the values are actually positive. Okay, if this is also positive, so ultimately what I am going to do, I am increasing the weight. Ultimately what I am going to do, that I am increasing the weight. Is it clear? Can anybody write yes, that you understood that if the y is positive, then I am increasing the weight? Yes? Who is writing yes? Okay. So let's see that second case where the y is equal to negative. If the y is equal to negative, this part is positive, this part is positive, and y is negative, then then what I am going to do, my weight is going to reduce. In that particular case, my weight is going to reduce. Okay. Now let me tell you, my system was wrong. In this particular scenario, my system was wrong. Answer should be positive, but the answer was negative. That's why it was wrong. Okay. What was the answer? Answer was the summation of this particular w's thing, na? Because I have find out where w0 x0 plus w1 x1 dot dot dot, where all the x are positive, it is negative. If I increase the value of w, then the total summation of this particular quantity would increase or decrease. Something is negative, you are try to understand. Right now the value is negative, it should be positive. So if I increase the value of w, then the value would come from negative side to, then the value summation would come from negative side to positive side. Okay, if I increase the value of w's, then my summation is going to become positive. I have a hope that the summation would become positive, and after some time, I don't know that how many iteration, but after some time, if every time I am going to increase, sometime it would become positive, and then my classification would be correct. Make sense? So I need to increase this. If my system is positive, if my item is positive, but my model is going to give it negative, then I should increase the weight. And this is precisely happening over here. So I assume that the things would be right. Let us see the second case. In the second case, what is going to happen? In the second case, item is actually negative. Item is actually negative. Item is negative, and my summation is going to give positive. Means my value is actually high, so I should reduce it so that it becomes negative. Na? I should reduce the weights, because if I reduce the weights, then the weights would become negative and everything would reduce, and then only I can get the negative one. Na? My system is telling negative right now, positive. I want it to give negative answer. This is a positive value, so if I reduce the weights, ultimately things are going to be the negative. So in the second case, when item is negative, my system is telling positive, then at that time I have to reduce the weight, and actually both the things are being done by this particular formula. So it is a fair assumption that after multiple iterations, because what I'm doing, for the right thing I'm not going to change anything, for wrong thing I'm becoming good, for right thing I'm not changing anything, but for wrong thing I'm becoming good. So ultimately what I assume, that after multiple iterations I would be able to get the right parameter. So this is the story behind this, that that how we can find out the right parameters. So this is the very important understanding. A few minutes back, we have also talked about that that the equation that we have written as a summation can be very easily written as a W transpose X. So for all future slides, I am going to instead of writing the summation of all the terms like this, I am going to write is as a W transpose X. That would be more beautiful to see. Okay. All right. I want to bring your focus to this particular quantity y multiplied by W transpose X. So here you know that W transpose X, don't forget about this. What is W transpose X? That my prediction of my model. Okay, W transpose X, if you want to find out, because W's are given to you, given a item, you want to find out this. If this value is given to you, this is the classification for your item. Okay. Let me find out that if I multiply this with the y, what is the value that I'm going to get? Okay, let us find out another quantity, that is a y W transpose X. What is this value? Okay, so there could be two cases. One case when y is equal to when my model is correct, and second case when my model is wrong. When my model is correct, then what is the value of y? What is the prediction of the model? Let me do this in this way. What is the value of y? What is the prediction of my model? Okay, when item could be positive or negative. When the things are correct, then my model is also give me the positive or negative. This is correct, this is fine. In that case, my model is also going to give the same thing. So here for y is equal to +1 and y is equal to -1, we have W transpose X is equal to greater than 0 and W transpose X is equal to negative less than 0, for because it's a right classification, na? So when the item was positive, when the y is equal to 1, then the W transpose X was positive. When the item was negative, then this value was actually less than 0. So if I multiply this y to this W transpose X, so positive is multiplied by something greater than 0, so the value remains greater than 0. If y is negative, and W transpose X is actually less than 0, if I multiply those things, what it becomes? That W transpose X becomes greater than 0. In both the cases, when I am correct, the W transpose X is greater than 0. Is it clear or not? Okay. Because you try to find out the multiplication over here. Okay. What is the multiplication of this? Okay. 1 and 1, it is 1. -1 and -1, it is again 1. So in the both the cases, it is greater than 0. What happened if it is if my system is wrong? For the +1, my system is going to give you -1. For -1, my system is going to give you +1. If you multiply these two things, it becomes -1, -1. So in the case when the things are wrong, when y is equal to positive, my system is wrong, then W transpose X is going to be negative. What does it mean? That if some items are there and you want to find out whether the classification is right and wrong, very easy test, that you just find out this particular value y transpose X, and if it is greater than 0, my item is correct, otherwise my item is wrong. Use those items for which y W transpose X are actually negative, and you update the value. Make sense? Okay. All the database is given to you. For every data item, you find out what is the value of y W transpose X, and if it is positive, then you need not to do anything. It is negative, means there is a wrong classification. Use that example to modify the values of W. It is fine. Any questions? All right. So this next slide is the same thing that we have discussed few minutes back, that it is perpendicular, that the weight vector is actually perpendicular. The same proof is there. You try to go ahead and try to understand. Okay, now I want to discuss a very important concept that actually try to tell you that this kind of modification that you are going to do, what modification you are going to do, this modification that you want to modify the value of Wi is equal to Wi plus alpha time yi xi. If you are multiplying into this particular way, it is not going to take infinite time. If the data is linearly separable, then you would be able to complete this processing within some speculated amount of time. So this is an important thing, that in some amount of time, after some time it is fixed, means it is not going to take infinite time to get converged, mean to give you this particular line. For that I am going to give you the proof. So to understand that, let me set up the environment, and the environment is this, that let's assume that you are hunting for this particular line, and the parameter related to this particular line is w asterisk. Okay, let's assume that the parameter related to this particular line is w asterisk. This is the right. Okay, this is the right parameter. Okay, that you wanted, but you don't have this value right now. You have only w, and w is you maybe you have got the randomly from somewhere. Okay. So my question is that you can find out one value that is y w transpose x. You can find out y w transpose x, w asterisk transpose x. Okay, because this now we have, I'm going to use the right one. You can find out this value. So what would be this value for all the points? It would be positive, because all the points are rightly classified. Now we have few minutes back discussed that this is going to give you, if this is going to be the positive value, because it is the right. I'm assuming that this particular w is right w, then this is going to be the positive value. So let me write, for every data point I am going to write that what is this value, y w star transpose x, what is the value of this thing I'm going to write. So one of them would have the minimum value, because many positive values, there would be a minimum, at least one minimum. Okay, maybe the two values may be same, 10 values would be same. At least I can find out one value that is a minimum. I can find out that value. Let me call that value as a lambda, no problem. Okay, let me call that value is a lambda. So this, let's assume that with respect to this particular point, the value comes to be lambda. Makes sense? For this particular point, the value of y w transpose y w asterisk transpose x is going to be lambda. Is it clear? This would be there, na? Because all the values are positive, so definitely I can find out the minimum. So for one point there would be some value that is minimum. That is only thing that we want to right now understand. Make sense? Any questions over here? This is the right parameter I want, but I don't have this parameter. Maybe I would be right now, my w is this, and I have to transform in some way so that I can get this. Maybe my line is this, I want to find out this thing. Ultimately I would reach to w star. Okay. Okay, so let me give you this problem once again. Let me go and show you what is the setting. W asterisk is the separating hyperplane. Mod of this particular quantity is 1. Few minutes back we have talked about that we can always set that this is going to be 1. It's not a big thing. Let's also assume that all the data points are actually normalized. So the maximum norm, any item that is farthest distance, is going to be only 1 only. We have seen that we can always do the zooming and normalization. We can also always bring the items into 0 and 1. This is not going to affect in any way the learning process. These things are fine. For there is the smallest value is going to be lambda, that we have also discussed. Consider that y w asterisk transpose x is greater than 0 for all the values, because they are positive. These things we have discussed. Now let us go to the proof. The first point is that when I do a update, means what, I had a w and I have changed it to the w plus alpha y x. I have changed to this particular value. Okay, this is the update. When I do the update, when I do this update, what happens, that it says that update increases this particular quantity, w transpose w asterisk. W asterisk is the actual value, by alpha time lambda. Okay, this I want to tell you. Let us find out the proof. Initial value is this. Let's assume that I do a update. By updating, this value transforms to w plus alpha time yx transpose, and then outside there is a w. This w goes inside w transpose w. This is the multiplication of these terms, and then it is multiplied over here. This term becomes what, alpha y w transpose x. Here focus on this particular part. Here focus on this particular part. This is the known quantity. Few minutes back we are talking about that the minimum value of this quantity is lambda. So this is minimum lambda. This value could be larger also. If I put here lambda instead of this thing, it is lambda, then this side, this complete side is going to be lower. So I can say that this particular quantity is actually less than equal to W transpose W star plus alpha time lambda. Can I write like this? So what it says that this is the previous value and it is added this, and this becomes the new quantity, because when you do the update, new quantity is going to be greater than this. Means at least it is increased by this particular quantity. Very simple line, one line. Okay, proof clear. Can anybody write yes? Yes, yes, very good. Next thing that I wanted to tell you, that just see that W transpose. If you consider on this particular quantity only single W, focus on say single W and its modification. So we want to say that it is not going to increase more than alpha square. Okay, alpha, you know that alpha is a learning parameter. So it is not going to increase more than alpha square. How can I show that? Initial, let's assume that this is the initial value, then I increase it. So what it becomes W plus alpha y x, alpha plus W y x transpose. What is the multiplication of this quantity? Can you find out? W transpose plus this alpha yx, this is multiplied over here, and when this would multiplied again, you would get the same term. So therefore 2 multiplied by alpha y W transpose x, then this is multiplied over there, it becomes alpha square y square x transpose. So you know that sometimes we put the transpose over here, and if it thinks that if you think that I'm not able to understand that how come this transpose comes. So try to always understand that whenever there is a vector multiplication, the right transpose would be always put into the right place so that the multiplication can happen. Okay. So hope this is clear, because this is just a single step. Initially you have W transpose, and after that what happens, that you got this particular value. Yes, say yes. Okay, let me tell you, let me keep this point so that we can compare that what was the earlier value was W transpose. This is the W transpose once again. What is the second part? See about this. This is here y multiplied by W transpose x, y multiplied by W transpose x. So this is again the same quantity. This is less than 0, because when we do the update, if we are doing the update, then this value would be definitely less than 0. Then only we are updating. No? Otherwise, why we are going to update it? If it is a wrongly classified thing, then only we are going to update. So value of this particular quantity is actually negative. So what is the maximum value? We want to find out what is the maximum value of this particular quantity. So if we want to find out the maximum value of this quantity, so can you tell me what is the maximum value? Maximum value is going to be 0 only. Okay, because it is negative quantity, maximum value would be 0. So we can neglect this particular quantity if we want to find out that what is the maximum value of this particular expression. Try to say another thing. It is alpha square, it is y square. So y is actually classification label. So y could be +1 and -1. Square of both the things is actually going to be 1. So this is 1. What is x transpose? You know that x is, we have few minutes talked about that x is actually normalized, and therefore if you do x transpose, you are going to get something that is actually less than 1. So what is the maximum value of this quantity? Is 1. Okay, so overall this second part, this second quantity, the maximum value of this particular second quantity, because this is 1, because this is also maximum value is 1, comes out to be alpha square. So we can say that this particular expression, this particular expression like this is equal to less than equal to W transpose plus alpha square. Fine. So let us write these two things. Let us write these two things, the first expression that we have seen and the second expression that we have seen. That when we do a update, W transpose W star actually increases at least by alpha time lambda. So let's assume that we do this update how many times? Let's assume that we do this update k number of times. So every time the value was increasing by k. Okay. So after k increase, what k increases, what is k time increase, what is the value of this particular quantity? It is k time alpha, because k time it has increased this thing plus something, some delta. So this particular quantity is actually greater than k time alpha lambda. So we can say that W transpose W star is greater than k time alpha lambda. So this is what it is, because k time we have increased. So this value is actually greater than this quantity. Okay. So what is this? What is this? This is actually, whenever we write the multiplication in this form, actually we mean that we are actually talking about its norm, because this is our understanding. And Cauchy-Schwarz inequality says that individual term, if you can find out their multiplication, this term is going to be larger than that. This is the Cauchy-Schwarz inequality. And here W, what is the value of W norm? We know that we have set it to the 1. So this is 1. This is 1. So it remains the only the W transpose norm of the W transpose. Norm of the W transpose or norm of the W is going to be the same. We can say that this is norm of the W. How we can find out the norm? It is just a multiplication of W transpose and take the under root. This is how we find out the norm. This is normal. This is the equation of the norm. So if we do the W transpose, every time this value is going to increase at most by alpha square. If k time we have done this increase, so under root of it is this particular quantity is actually less than under root of, because this value is k alpha square. Now we have equation k time alpha lambda is actually less than under root of k alpha square. So k square alpha square lambda square is less than k alpha square. Okay, alpha square goes away, and I think k also goes away. So k alpha lambda square is less than 1. So we can say that k is less than 1 upon lambda square. Okay, can find out this equation. K is less than 1 upon lambda square. And you know that what is this lambda? This lambda is a property of the data. This is not something that we have actually come up. If there is a data and we assume that there is some right thing, then there must be some lambda. This is dependent upon the data only. So actually data dictate us that how much steps is actually required. After this thing, the things are going to converge. After this many number of steps, the system is going to converge. Why? Because the W that you are going to get becomes correct. For all the values, it is going to be correct. So you started with any W, you updated this multiple number of time. How many time? At most 1 upon lambda square number of time, and your W becomes W star. And this is what the proof that ultimately you would be able to stop and you with the right kind of parameters. So this is the proof. Any questions on that? So okay, so this is very this once again I just request you that in you see the recorded. Sir, can you please show how we get k alpha lambda is less than alpha star lambda is less than W transpose W star? Where is that formula? You can speak also. Where is the formula? Formula number 1 or 2? Which formula you are talking
So
about? 1 or 2?
that is derived from the first formula after applying k number of times. First line.
This part?
Yeah, yes, sir.
This line? Okay. So this line is very simple. Okay, let me tell you what happens now. Let's assume that there is some W you have. 1 minute. Sorry. So what happens now? There is some value. I don't know that what is the value of W. Let's initially, I don't know that what is the value of W transpose W star. I don't know that what is this value. Okay, initially because my W is not set, but you know that W star is set in somewhere. Let's assume that because of the data, it is being dictated that this is the right parameter. So let's assume that W star is somewhere fixed. Makes sense? That W star is somewhere fixed. I don't know that what is the value of W, so I started with some value. There is a multiplication, so this multiplication would be some delta. I don't know that what is this value. Let's assume that this is delta. But if I update it, we have shown that if W becomes W star W dash T, new one. So what would be the value of this quantity? It would be delta plus alpha lambda because of this particular formula. If I again update it, W star W becomes W double dash transpose. So this value becomes W plus alpha delta plus alpha delta, because every update is going to at alpha delta. So after k update, what value is going to be added? K time alpha lambda. This value is being added. So the overall quantity is actually going to be delta plus k time alpha lambda. This value is going to be, okay. Make sense? So delta plus this. So if I remove this delta part, I can say that this W transpose W is asterisk is actually greater than that particular quantity. Make sense?
Sir,
Yes. Okay.
sir, isn't
Yeah.
W is the starting vector
Yes.
with
W
which?
is a starting vector, but W star we think that based on the my database, it is the right parameter.
So at last, when it converges, W becomes W star, right?
Correct. That I mentioned few minutes back, that we start with any W, but after multiple iterations, after k number of update, it becomes W star.
So finally, we will be getting an equation like W star transpose into W star greater than or equal to the
Correct, for all the
previous.
data items. Yes. Yes.
Sir, sir, I have doubt like whether the iteration mean like in the second iteration would should we have to write like W plus 2 alpha yx transpose into W star greater than or equal to W plus y alpha yx
No, no, you need not
transpose.
to. No, no, you need not to write, because all those things are incorporated into the W itself. Because W is of that particular quantity kind only. Because if you are going to do the updates, all those things are actually incorporated into the system. That we have shown here only. The procedure is only using the W. Procedure is only to use to update the W using the update rule that we have. That is very simple update rule. A few minutes back we have discussed that this is only the simple update rule. And inside this if you look mathematically inside this thing, you would be able to understand there's these two properties that we are talking about. They are inside this particular expression. All these things that we are going to see, they are the just explanations of this particular equation only. Okay. So you by yourself is only updating W every time, but this update is actually going to bring you every time near to the W star. And after k number of updates, you would be W star. So W would become W star, and it is W. In your terms, you are having a parameter W, it would be W only.
Okay.
Okay. Okay. Thank you. So this is the case, and when you get the right parameter, and sometimes you are not that much lucky, and your data is not linearly separable. If the data is linearly separable, then only you can apply this thing. Please note that whatever convergence proof we have done, it would be utilized at the later point of time into our course. So please go through this, try to understand this. Later we would see that what is the perceptron convergence rule. In there, these proofs are going to be utilized. So what I told you, that it may not be the easy task to do. Sometimes it may be possible that your data is such that you cannot actually divide into that particular using a single line. You cannot divide into the two parts. So definitely there would be some problem for the items which are actually not onto the right side. For example, if I give you this thing, let's assume that I give this data. Okay, asterisk and 0 0 0. Now you can draw a line, but if I put a 0 over here, x over here, you cannot find out any boundary that actually divide these things, linear boundary divide these things. Okay, so even if you come up with this particular line, that is perfectly right, because this is the best that you can do. There would be some places where there is a problem, and that problem is mathematically notated, is represented as a loss. So if you want to find out that what is the performance of your system, so performance actually means that how close your predictions are to the actual ground truth. Okay. So closeness you want to find out of your given function, that is called hypothesis, with respect to the target function. So if you want to compute the loss for your particular function, so you see that at how many places your system is not going to give the right answer. Okay, you count that. Okay, you count that at how many places this is my system is not going to give the same answer as the actual answer. You say one as those places and count. So in the previous example, answer would be 2, because at the 2 places it is not going to give you the right answer. Similarly, there are a few problems where you actually, instead of just saying that this is the classification, you give some value. This is a regression kind of problem. into the regression problem. If you want to find out that how good I am, then you have to see that what is the value given by your thing and what is the actual value, and you square that, and then by this you would be able to get some numerical value. And then for the places where you are not going to give this exact result, you are going to find out the summation of this particular quantity. Otherwise 0 needs not to be written, as you know that otherwise what would happen if they are not same, they are same. Otherwise case is actually what, that hx and yx are actually same. When they are same, this quantity itself becomes 0. Why to write that? But just for the sake of understanding, I'm writing this, otherwise it is 0. So this summation of this thing, it is called SSD, sum of square distances. So ultimately what happens, that you start your procedure is to start by some w, and that is going to give you some loss, and after that you update the value of w. Now your loss is decreasing and you keep decreasing the loss, and at the end when your loss becomes 0, you stop and say that these are the parameter. On the training data, if you do that, because you know that you have a database for the learning. On the database, if you do that and you reduce the error, this particular task is called empirical risk minimization. This is called empirical risk minimization. And what is your objective? Your objective is to reduce the generalization error. Actually you want to, because whatever unseen examples are on that, because if you have a model over here, if you developed a model over here, you can assume that this model is applied on this data also. And however this is not exposed to you, the new things are not exposed to you, so whatever data is there, you base on that, you have actually computed the loss. If you modify your model parameters so that it becomes better suited to your data, you think that okay, on this also the error, let's assume that here the error is 80%, okay, and here the error is 70%. So if you are changing the model and your error becomes 60%, you are expecting that here also the error would become 55% or so. Here also the error would be reducing, but it is not directly related. It may not be directly related, but actually the problem is this, that you cannot do anything else, because only this is the data that is available to you, because only the training data is only available to you. So what you can do? So there is no way to go beyond that. You have to do empirical risk minimization in a hope that you are actually going to reduce the generalization error, and this is called the generalization error, and this is called the empirical error. So there is no other way to do that. So you understand that what do I mean by empirical risk minimization? That actually you want to reduce the error on the training data. And what is the generalization error? That is related to the unseen things, and you actually expect, you are into hope that this is also going to be reduced. A few minutes I have, so I would like to bring this particular interesting example to you. And this is what I'm going to talk about, the matching scores. Okay. So let's assume that this is the person, 1, 2, 3, 4, 5 people are there. And on the next day when they come, their image is this. If you take every day their photograph is this. So you can see that all these photographs are different. So let's assume that in my database, I have stored this particular image. Whenever next day this person comes, because I don't know that who he is, I would use this image to match with all other things and try to find out that on which image it is going to give me the highest value. And I would say that because you know that this image would give maximum value over here, this is expected. This may not happen all the times. It is expected that it would give maximum value into this particular case. This would give maximum value with this image. So this is actually by this, when you are comparing these two images, you are going to get the matching score. Matching score could be similarity or dissimilarity. When the two things are matching, the score is actually high, then it is called the similarity score. What is the dissimilarity score? You take any maximum value and reduce that value from that. This is a dissimilarity score. Matching score are of two kind, genuine and imposter. What do I mean by this? That you use this image and match with this, score is 0.8. You use this to this, score is 0.5. This with this 0.4, this with this 0.45, this with this 0.51. So when you are matching this person with the same person, this is the genuine score. This particular score is called genuine. When you are matching this image with the other things, it is called the imposter score. This score is called imposter score. What is the value, we would analyze later. It could be larger and smaller. Try to understand that what is imposter score. Imposter score, that when the two images which are involved for the matching, they are not of the same category, but not of the same person. Okay, score can be normalized. So see, this first person first image is matched with the first person second image. So this image is actually matched with this image, and it is a genuine match because same person are being matched. It is genuine because same person are going to be matched. Okay, this is the genuine score. Why genuine score? Because this is the first person, this is also second first person. So this is the score. So score could be anything. So concentrate on this third person second image. Third person second image, this is matched with the fifth person third image, for fifth person third image, this image. Okay, third person second image is matched with the fifth person third image. This and this are going to match. Okay, going to be matched. It is a imposter because they are the different person. It is imposter, and this is what the score is. Okay, so if I match this with this, try to understand. If I match this and this, I got 0.5. If I match this with this, I may get 0.45. So scores are generally not commutative. What I wanted to tell you, that we can plot this over here. Okay, if we segregate all the genuine scores, if we segregate all the imposter scores, we can plot it and see that what is their histogram. If this is the histogram, so if let's assume that this is the histogram of, this is the genuine scores and this is the imposter scores, so how can I decide that whether when two images are matched, whether they are matched or not? So I have to decide based on your threshold. I have to draw a threshold on that, and if the score is greater than this, I say that they are same. If score is less than this, I say that they are of the different person. So if this is the threshold, these are the score that I obtained from the genuine peoples. So these scores is actually lesser than that particular threshold, but they are coming from the right persons. So these peoples would not be able to access the system and they would be rejected. But this is a false reject because this is a wrong result. So this thing is called the false reject. Similarly, this is the imposter, means wrong peoples are matched, and if this is the threshold, that these scores are actually greater than the threshold, so these matchings are going to succeed. This is the false acceptance. This is the accent because they would be accepted to the system, but this is a false acceptance. This is a wrong acceptance to the system. So two kind of errors can happen when we are going to develop what? False accept and false reject. False accept is called type 1 error and false reject is called type 2 error. So if I ask you that what is type 1 and type 2, would you be able to tell? Type 1 is false accept and type 2 is false reject error. Okay, type 1 and type 2 error. Okay, which error is more problematic? Type 1 error is more problematic because he is the person who is the wrong person who has got access to the system. What he is going to do into the system, I don't know. So that is a wrong thing. Here is only the problem. Type 2 error is a problem because somebody who wanted to access, he is not going to access. But if he is a genuine person, he can do the another attempt, and in the another attempt, his face would be maybe more visible and better thing, and he would be able to get the answer, get to enter to the system. So T2 is problematic but not going to harm to the system because he is the right person. When he entered the system, whatever he does is the right thing. But if T1 is a most problematic thing, so can you tell me that for the high security system, what should be the threshold? This should be the threshold. Okay, many right people are standing onto the gate, they are not able to enter, but the wrong person should not be able to enter. They are very less. Okay, but for the low security situations such as going to shopping mall, etc., if you want to deploy a security system, everybody should be able to enter. Very few people should be restricted to get the access. So this is going to be the smaller. Okay, you have to reduce the, you have to keep the threshold low. So I think that's all for today. Few more slides are there, and very quickly we can cover into the next class. So thank you very much.